Dear students, after studying this module, you shall be able to know about the protecting groups. Study the characteristics of the protecting groups, understand the functional group protection and know the protection of the important functional groups. Protection and deprotection is an important part of organic synthesis. During the course of synthesis, we many times desire to perform a reaction at only one of the two functional groups in any single organic molecule. For example, in an organic compound possessing two functional groups like ester and ketone, we need to perform a reaction at only the ester group. Then the keto group needs to be protected. If we want to reduce the ester group, then keto group will also get reduced. To avoid these type of complications, protection and deprotection of the functional groups are necessary. Protecting groups for the carbonyl compounds. The protecting groups allow the masking of a particular functional group where a specified reaction is not to be performed. The protection is required as it interferes with the another reaction. Let us take the example of reduction of the keto ester represented by the structure 1 to alcohol as structure 2 with the nucleophilic reagent such as sodium borohydride that attacks only the more electrophilic ketone. In order to make the alcohol 3 by the reduction of the ester, it is important to produce the ketone as an acetal that allows the reduction of the ester with the nucleophilic lithium aluminium hydride. As can be seen from the structure, for this difunctional compound, if the reduction takes place in the presence of sodium borohydride, the double bond gets reduced to form an alcohol. However, if the ester group is to be reduced to an alcohol, what should be the probable mechanism which should be carried out? If you look at the another figure, the groups can be protected, a keto group can be protected and then the reduction takes place. Finally, the deprotection leading to the formation of the desired compound. In another example, 3-oxocyclohexane carboxylic acid methyl ester 6 undergoes the reduction with lithium aluminium hydride to 3-hydroxy methyl cyclohexanol represented by the structure 7. If we want to go for the selective reduction, then the role of protection and deprotection comes. As can be seen from the given reaction, the reduction of 3-oxocyclohexane carboxylic acid methyl ester with lithium aluminium hydride gives 3-hydroxy methyl cyclohexanol, that is the ester group gets reduced. During the protection, ketone from the compound 3-oxocyclohexane carboxylic acid methyl ester forms ketols on reaction with methanol under the acidic conditions. The protection reaction can be reversed by treatment with the water under acidic conditions. Henceforth, in the given reaction, it can be seen that in the presence of methanol, the ketols are formed at the keto position. The reduction in turn leads to the reduction of the ester group. Finally, the deprotection with the acidic hydrolysis gives the desired keto hydroxy compound. The characteristics of a protecting group are as follows. It must be easy to put in. It must be resistant to reagent that would attack the unprotected functional group. It must be easily removed. The protecting groups for alcohols. Methyl ethers and simple amides are also easy to synthesize and are quite resistant to variety of reagents. From reactions, we can see that the reaction takes place to turn R1 in 13 to R2 in 16, but the protection is not very helpful as extreme conditions are required to remove them. These can be used when the molecule is stable enough to bear the deprotection conditions, as represented here in the figure. The alcohol R1OH in the presence of a base and methyl iodide leads to the formation of an ether wherein the reaction takes place for the substitution of R1 to R2, and finally the deprotection by using refluxing medium in HI leads to the formation of R2OH. The Achilles heel strategy. The Achilles heel for the functional group ether is use of the tetrahydropyryl group THF. This converts the ether into an acetal. The compound used to give THP derivative is dihydropyran, represented by the structure 24. The protonation of dihydropyran yields the compound with the positive charge on oxygen, as can be seen on the structure 25. This is further reacted with the alcohol ROH to give acetal 26, shown in the figure. The compound 2-methoxy tetrahydropyran, where R is CH3, is known as the THP derivative. The protection of the alcohol from the protecting group, hydrolysis only requires a weak aqueous acid. We can see the given scheme in the figure 5. There is another way to make the ether easier to eliminate, is to convert it into benzylic form as given in the figure. The alcohol can be protected as a benzylic ether and easily deprotected to give the desired product. For example, alcohol 27 on reaction with benzyl chloride in the presence of a base like sodium hydride gives alcohol protected as benzylic ether. We can do any reaction on the protected alcohol group, and deprotection will be done by the simple hydrogenation in the presence of the catalyst. Other popular method to protect the alcohol group is to convert it into trimethylsilyl ether. This can be done by treating the alcohol with chloro-trimethylsilane and a tertiary amine. Protecting groups for amines. Amines are the compounds that exist as RNH2. They are further classified as primary, secondary and tertiary amines based on the number of substitution at the nitrogen atom. In all the cases, nitrogen possesses an unshared pair of electrons that causes the problems in synthesis. This requires protection. The amines are mainly protected as amides and carbamates. The conversion of amine to amide decreases the activity of the amino group. Amine can be easily converted to a corresponding amide form using acetyl chloride as shown in the figures. The formed amide, or we can say the protected amine, undergoes the desired reaction to get converted to the structure 19. The deprotection of 19 can be easily done with sodium hydroxide to get the free amino group. Another example is the bromination of aniline. On brominating aniline, represented in structure 21, the 2,4,6 tribromo derivative is formed. As we can see, the yield is quantitative, but we want monobrominated product, and for that the excessive bromination needs to be stopped. To overcome the excess bromination, the protection of the NH2 group is essential. The acetylation of aniline converts aniline to acetyl aniline, represented by structure 23. The Mi23 on bromination gives only bromine at the para position, that is N-acetyl group is larger than NH2 group, and the hydrolysis does not destroy the benzene ring. Other protecting group includes carbamate. This is also an amide bond, but with some other functionality attached that allows them to be removed under the mild reaction condition in comparison to the simple amide group. For example, the reaction of a primary amine with tertiary butyl chloroformate forms a carbamate under basic condition. The protected amine can undergo any reaction and further then deprotected to give the desired product. To summarize, the protection and deprotection is an important part of organic synthesis. Protecting groups allow masking the distinctive chemistry of a functional group as it interferes with the another reaction. The characteristics of protecting groups are as follows. It must be easy to put in. It must be resistant to reagents that would attack the unprotected functional group, and it must be easily removed. Ethers and amines are used as protecting groups when a molecule is stable enough to bear the deprotection condition. Alcohols are usually protected as ethers, whereas amines are protected as amides and carbamates.